Have you been struggling how to treat a coupled force when you're trying to solve the reactions? Let's have a look at two cases in this following exercise. In the first one, we have 2 point loads which give a coupled force and no moment. In the second option, we'll have that same coupled force with a moment. Let's see how to tackle this problem together. So, as I mentioned, the first exercise has this beam here. Let's call this A and B. And as you can see, we've got these 2 point loads, P and P. They are equal in value, but opposite in direction, and they have a distance between them. That means they give us a coupled force, which means that the moment they produce is equal everywhere. Now, in our first case, this moment is 0. So just so we don't get confused, I'm going to delete it quickly. There we go. No moment there. Let's solve the reactions together. So the first thing that we want to do is we want to create a free body diagram. So here we can see that we've got a pin support. That means 2 reactions, AY and AX. And at B, we've got a roller support. So in that case, 1 reaction of BY. And now that we've got our free body diagram, let's solve the reactions in this case. I'm going to start off with the sum of forces in x equals 0, with this being my positive direction. So in this case, I've got AX and nothing else in the x direction, so AX has to equal 0. The next thing that I want to do is sum of forces in y, so sum of forces in y equals 0, with this being my positive direction. In this case, going from A to B, I've got AY in the positive direction, minus P, plus P, and plus BY. Nothing else in the y direction, so that has to equal 0 to be in equilibrium. And I can see that the p's cancel each other out, so I'm left with AY plus BY equals 0, or AY equals minus BY. And the last thing that I want to do is sum of moments. So let's do sum of moments around A equals 0. Now, if I recognize that this is a coupled force, which I do, they are always going to contribute the same moment, regardless if I'm at A or at B or any other point in my 2D plane. Therefore, I just know what this moment is. Now, I can see that these two forces, if I just draw them here, one is going that way, one is going this way, and I can see that they create this circle, right? So this is the rotation they create, and I can see that that is positive in our sign convention. The moment is always going to be the value of the force times the perpendicular distance between the forces. So the value of the force times this distance. So in our case here, what I can say is that I've got a positive moment, and that moment is P, the value of the force, times 0.5a, right? This distance here, the perpendicular distance between the forces. And the only other thing, apart from those two forces contributing to moment, is that reaction at B, which also gives me a positive moment. So that is plus by, and this time the distance is the whole distance from A to B, so times A equals 0. I can see here in every part of this equation, I've got force times distance, force times distance. So I know that I'm in units of moment. What I can do here is I can divide everything by A, and I am left with By equals minus 0.5p. And now the last thing that I want to do is go back to this equation and find that AY equals minus BY, so it's minus 0.5p, and therefore AY equals plus 0.5p. And as expected, these are in units of force. Now, if you hadn't recognized that that was a coupled force, would you still have gotten the same results? Yes, you would. Let's just have a look at the moment at that very last equation. If I do that, if I just do the sum of moments around A equals 0, with this still being my positive direction, and this time I haven't recognized that this is a coupled force, so I'm just going to solve it force, force, force. Starting with that first P, it gives me a negative moment of P times 0.25a. The second P gives me a positive moment of P times 0.75a, and that reaction still gives me a positive moment of By times A equals 0. That means that here, if I add up the first two members of this equation, I get P times 0.5a plus by times a equals 0. And I can see that just with a couple more steps, I have reached exactly the same equation that I reached here. So If you haven't managed to recognize that it's a coupled force, don't worry, it'll still come out in the wash, you'll still get the same results. But if you have, then you've saved yourself a bit of trouble, and if you have multiple coupled forces in your structure, you'll have saved yourself a lot of trouble. The last thing we need to do, obviously, is put the forces back in the structure. So AX, we already said, was 0, AY worked out as plus 0.5p, and BY worked out as negative 0.5p, which means that I just assumed the incorrect direction and really it's in this direction. Now I can see here, just if I want to do a little check, that I've got two coupled forces. I've got this first coupled force that gave me a moment, so let's call it m1, of plus p times 0.5a, or we can write that a bit nicer as 0.5pa. And we see that the units here are p, force, times a, distance. The second coupled force, let's call that m2, gives us a negative moment, right? Because it is turning in the opposite way. So in this case, we've got minus 0.5p, that's the force, times the distance between them, which is a. And what we can see here very clearly is that these two moments balance each other out. We are definitely in equilibrium. So we managed to solve a beam with a coupled force, and we saw that if you can identify the coupled force, it makes solving the beam easier, and if you couldn't identify it or you weren't too sure, you could check yourselves and still get the same results. Let's see what happens when we throw in another moment into the mix. Let's have a look at this exercise again, just with a moment in the middle. Okay, so what I want to do now is solve exactly the same exercise, only this time with a moment. Now, I've been told that this moment is 0.5pa. I can see here units of moment, p, the force, times a, the distance. Let's see what happens now. So first thing we're going to start is getting that free body diagram. We've already done that. We know that here we've got AY and AX, and over here we've got BY. I'm going to start off just like I did before with a sum of forces in the x direction equals 0. So I've got AX, and once again I haven't added any forces in the horizontal direction, so AX has to equal 0, and that's that first one solved. Moving on to the sum of forces in the y direction equals 0. This hasn't changed either, because I've added a moment, I haven't added a force. So once again, I've got AY minus P plus BY equals 0, and I can see here that once again, AY plus BY equals 0, or AY equals minus BY. The only place where adding the moment does influence in the reactions is the moments. So let's do moments around A equals 0, with this being my positive direction. So once again, I'm going to start from A to B and see what we get. So I've already recognized that I have a coupled force. Okay, so in this case, I've already discussed that it is plus p times the distance between them, so 0.5a. Then I've got this moment. It contributes a pure moment, so I only need to take into account the moment. There's no distance to take into account here. I can see that it is turning clockwise, which means negative, so minus 0.5pa. And I've got a moment from by, so that is plus by times a equals 0. But what do I find here? I find that adding these two gives me 0. So actually I've got by times a equals 0. Now I know that a is a distance, so it's definitely not 0, and therefore by equals 0. Now if by equals 0, and I go back to my equation here, where ay equals minus by, ay is also 0. And all that means that in this case, this moment here has balanced out the moment from these two forces, this coupled force. They've balanced each other out, and the reactions are 0 because the forces have balanced each other out without the need to add reactions to create equilibrium. So recognizing the coupled force in this case made this much quicker to solve. We could still solve it the same way that we did before, and we would get the same result. Let's do that quickly just to check. So if I say sum of moments around A equals 0, and I just do it force, from the first force I get minus P times 0.25a, then I get the moment, so minus 0.5 pa, then I get this additional p, which is plus p times 0.75a, and then I have that force, so plus by times a, and all that has to equal 0, and we can see that these two add up to plus 0.5 PA. The next thing, the moment, gives me minus 0.5 PA plus by times A equals 0. So I end up in exactly the same place. So now, if I want to add on the results for my free body diagram, all I have to do actually is get rid of these, and that's it. This is my balanced beam. Now, I am kind of sorry to say that I did give this exercise in a coursework once to students, and I did make some students cry, because I think when they got a result of 0, they thought they were doing something wrong. It just means that you need to try and understand how the structure works. If you get 0 or you get an unusual response, that might be okay. Just do a check and make sure that you get the right result. Checking yourself is pretty easy when you do reactions in a statically determinate structure. And that's it for now. I hoped it helped get over any fear of coupled forces or getting any fear from 0 reactions. A bit mean, I agree. But that's it for now. See you in the next one. Bye for now.